What's up guys, welcome to today's show. Now we need to create assembly code because this code does not use the special Intel instructions. So we need to create an assembly program which does. And it shouldn't be too advanced. The only problem as I see it is that we will be dealing with 128-bit CPU registers, even on a 32-bit machine like mine. So that might be a little bit tricky because we need to use some special instructions to deal with 128 bits. But I think the AES instruction itself, I have the Intel manual here. It is called AES KS assist. And it takes 3 arguments. XMM, that's the name of these 128-bit registers. So this first one is the destination. The result will be stored inside of this. And this is the source, which is either this CPU register or a memory address pointing to a 128-bit value. And then the third is the round constant. If you remember, we created this function, this rconst. So we will need to supply the value of this. So not the round per se, but the actual round constant. So it's good we made this function because that will make things a little bit simpler. Right, so let's begin and see where we get. Alright, so new file, and let's call this AES key schedule .asm. So this is going to be the AES key schedule ASM version. So what do we need? We need somewhere to store the output, the return value. So let's say we have a section for BSS and here we can have a label. Let's call this output. And we want to reserve 16 bytes. 16 bytes, that is 128 bits. So here we'll store the result. We can do this, but while we are experimenting with this stuff, we can have a data section as well. And here we will store the input for now. We can't really reserve here, so let's do times 16 define byte 0. Okay, so now we have 128-bit for the input and 128-bit for the output. Let's also tell the assembler that we are using 32 bits. And we will only export the function we're going to use, but for now it will be a little bit easier if we export the start label, because this is where it's basically the main function, but for ASM. So we'll have a text section which is for the code, And here we will put our start label. Let's start by cleaning out, it's the XMM1. So we can't just do move into XMM1 0 because those regular instructions don't work on these weird 128 bits. And we can't do XOR either, but we can do P XOR, which is basically the same but for these kind of weird registers. So this will clean out the XMM1 register. And I have a couple of manuals up here. Move DQU is used to move data into those XMM registers and to them from a memory location or to a memory location. So this we will also use. Let's consult the manual. So, alright, XMM1 is the destination. So this is what we'll use. Here we can use the memory address. And here we have the round constant. So, because this, when we created the C version, then we just called generate keys and it created all 11 subkeys. This AES keygen assist only creates one subkey, so we need to call this 10 times or 11 possibly. But we'll do that. We'll call our own assembly function those number of times, so we don't have to worry so much about it here. Alright, so we want to do this AES keygen assist. And we want to store the result in XMM1. And the input is going to be this. So a memory location. So this will be an XMM word, that's it. Because we need to specify the size. And this is going to be an XMM word size, that's 128 bits, pointer at this memory location input. And then we have the round constant, which is 1 for the first round. Well, and this is basically it for just doing static values like this. But now we have the result stored inside of XMM1, and we need to copy it into our output buffer. So now we need to use this move DQU, and the destination is going to be an XMM word pointer output, and the source is going to be XMM1. Maybe we need to tell it it's an XMM word here as well. It should be able to figure that out, but you never know. And let's create an exit label where we move into EX1, we move into EBX0, and we call int0x80. Alright. Let's see if this assembles or compiles. So we are going to do NASM, and we want to create an elf of this AES KS.asm. Comma colon decorator or end of 15 and 16. Maybe it doesn't like that we have this right here. And here. Is it like this perhaps? I haven't been working a lot with these kind of registers. Maybe we just do this and it figures out that it's a XMM word pointer on its own. Okay, no error this time. Good. And how does an obj dump look? Alright, so first we XOR out this thing. Then we run AES keygen assist against XMM1, XMM word pointer. Okay, so I typed the right thing, but apparently it didn't like that. DS0 doesn't look so great though. Maybe need some colons. Let's also jump out a little bit here. Do the same here. It still becomes a 0. DS0. And this doesn't look right either. Let's see if we do read elf on this thing. 0 program headers. Maybe we don't have the dot here. I don't really remember. No, we did it the right way in the beginning. I think it has to do with that it's only an object file for now. We haven't really created an executable, and that's probably why. So it hasn't really decided what memory addresses to use. That must be it. Right. Okay, so let's try to do that then. And let's link this thing. So we do ld AES O-O AES like this. And if we read elf this thing, okay, now we have 3 program headers. And what's the flag for listing those? Here. Okay, so we have one which is read-write, that's our date. That's our BSS, I guess. And we have read and executable, which is our text segment. And then we have a read only as well. Probably some information or so. Right, let's just see, can we run it without segfault? That's always good. What's the return value? 0, alright. And if we were to do an obj dump on this thing then, alright, that's more like it. So we clean out XMM1, we run this AES keygen assist, storing the result inside of XMM1. We use this address 4A000 4A000, so it's this input thing right here. Then we copy the result from to this memory location 018, which is the output. And we copy from this right here. And then we exit. Alright, we need some GDB. So we'll go into TMP key schedule. Let's set this to our home. Let's cat GDP. And let's copy my configuration line by line. If any of you figure out how to let it auto-load a configuration like this, please let me know. Primarily so I can remove all annoying colors. We define F, which is target exec, and target exec AES key schedule, and also set the symbol file to the same. End. And I also want to define my XX macro, which does x/30i on EIP minus 20. So basically this will list the instructions where we're at in the program flow. So let's see, let's start, and I want one more thing, I think. Define clear. Yes. And it's gonna run clear like this, and works. Okay, so let's start this thing. And let's break on start, run. So we are here. And let's see. We want to go here, so step I. So we are just about to copy the result into our piece of memory. So let's first check how our memory looks. 16 bytes here, all zeros. Okay, good. So now we do step I, and now it should not be all zeros any longer. And it's not. But it looks a little bit funky. 63, 63, 63, everything is 63, almost, but this. So, should it be like that? Or has this something to do with the backdoor? We don't yet know. It would be a little bit interesting though to see what will happen if we give, because now we are using a zeroed key. So what if we do the same here? And then we check the first line. So here is where we're at. 62, 63, blah, 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 blah. All right, looks like we are on the right path. All right. So now we need to create some functions so we can call this later on. So let's say we have a function called, I don't know, ASM key schedule. And ASM key schedule is of type, what do we need to send to this? Well, we need to have the input key. And that should come from a memory location. So basically, well, it's a int128 pointer basically. And we also need to have the round constant. So that will be an int 8. And we are going to return an int128 pointer as well. And by int128 pointer, what I mean is a pointer to a memory location with 128 bits. All pointers are 32 bits wide, at least on 32-bit systems like mine. Okay, so we will basically do similarly to what we did up there. Let's zero out this register. And let's say that we have inside of EBX, we have the input. Inside of ECX, we have the round constant. And we want to return it by putting it into EX. Like so. Right? So first we clean out this XMM1. Let's also clean out XMM2. Or do we need to do that? Let's see. Input. No, I don't think we do actually. We don't need to do all that much actually. I think we can call this, and we still want XMM1 to be our destination. And what will be our input? That's inside of EBX. So we should be able to do this, I think. To just go to that memory location. And the round constant should just be ECX then, I guess. So now we run this thing and we want to move DQU to the output. And we can store it inside of the BSS like we do right now actually. So let's just do output. We go from XMM1. But now we need to return the address to this output data location. So let's move into EX the address of output. And then we'll return. I think that's going to work. We can try it by putting the stuff inside of these registers. So inside EBX will be the address to our input. Inside ECX is our round constant, so let's put 1 there like we did up here. And instead of just returning here, we can call exit temporarily so we don't crash. So this should basically be the same as that we had, but now it is a function which we can use. We should even export this thing, right? Global ASM KS. Let's see if this compiles. Maybe we should alter this make file so we don't have to do this manually all the time. So we have an AES key schedule AES key schedule.asm. We're gonna run nasm elf, or maybe we can do it like this. Looks a little bit nicer. So asm flags, and we want to take our input. And when we have this thing, we can create AES KS. And our dependency is AES KS.o. And we're going to run ld input file -o output file, like so. And we need to update this clean as well. So we need to remove AES KS as well. And we want to put AES KS here as well. Alright, let's see what's happened. First, can we clean out everything? We can. Can we run this now? Line 25. Okay, we cannot give the EBX like that. What if we add those prefixes, XMM word this? XMM. It compiled without errors this time, but it didn't find our start. That's a little bit weird, no? Let's try it again. Okay. So if we can't use EBX like this, what can we use? M128. Does that mean we should store the memory address inside of a 128-bit register? Could that be it? Or a 128-bit memory location? Well, we can try. So let's clean out XMM2 as well. And then we move DQU. Into XMM2, and what do we want to move there? Well, we want to move whatever is inside of EBX. No, we want to move the address inside of EBX like this, and then we want to call it like so. Let's see if that works. Nope. What if we just do move D? That did work, but this still doesn't take a memory address like this. What if we copy the contents instead? So if we do move DQU and whatever's inside of EBX, is where we... No, wait a second. We want to move into XMM2, whatever is inside of EBX. And then we can use this register like this instead. So here we copy the contents of the input into this XMM register, and then we deal with two registers like this instead of like we did before. Let's see if this works. As I promised, the problems would have to be related to those registers. The rest seems quite easy actually. 27. So now what's the problem? Is it this ECX thing? The round constant. Im8. 8. Okay. So now it's a 16-bit register. Now it's an 8-bit. Still complains about this one. XMM1, XMM2, that should work. But Im8, immediate byte. That must mean that we can't even use a register there. Which complicates stuff quite a bit. Let's just double check that this is really the case. If we were to put a 1 here, then it compiles. Tricky thing. So basically we need to hard code all the different round constants. Let's see if the manual says anything of value about this. Well, we could do it similarly to this. We just go through all the different round constants and create the entire thing instead of just one. I suppose it's our only option. I wonder why they did it like that. Alright, let's do it like this then. So let's see, we have our input and our output is this thing. So we basically need to create 11 of those then. And then we need to copy the stuff into the current place in that array. So that's basically this line. But let's put that in its own function. So let's see. Let's call it copy res. And let's store this pointer somewhere. We'll reserve a double word for this. Let's jump out a little bit here. So this will be our init. This will be our copy res. So when we initialize, we can move into EDX our address to the pointer. We can move into EDI address of the output. Let's see, EDX pointer. Let's start with this output. So into EDX, we move the address of the output. Into EDI, we move the address of the pointer. And then we move into that location, EDI, whatever's inside of EDX. So now we have saved the address of the pointer into, the address of the output into this pointer. All right. And then we run all of this. Let's call this return. Comment this out. Alright, so at this point we need to get the current pointer. And we can't touch EBX or ECX. We don't really need to use ECX though, because we don't need to specify the round constant any longer, since we will use all of them. So all we need to do is to give the AES key. Alright. So move into ECX. The address of the pointer. Move into EDX. That address. So now we know the current address of the pointer, and now we want to copy our stuff there. So we want to do a move DKU into EDX like this. XMM1. So now we have saved the result, the return value basically. Now we need to add 16 to the pointer. So add to, let's see, ECX contains that, EDX contains the address. So to that we add 16. That's because each key, subkey is 16 bytes, and we want to move to the next one in the array so we can save it to that one, the next iteration. Alright, and we also need to put it inside of that pointer. So move into, let's see, EDX is the address, ECX contains the pointer. So we move into ECX, the EDX. And what else do we need to do at each iteration? So XMM, let's see, XMM1 contains the new subkey. But we read the input from XMM2. So we need to, let's clear out XMM2 and let's move DKU, move DQU, into XMM1 we want to put into XMM2 we want to put XMM1. And since XMM1 is going to be the output, we want to clear that out now. And then return. I think that's correct. So let's remove this. And we clean both of these. Move into XML2, the contents of EBX. This we don't need to do each iteration, so let's put this inside of the init instead. So we run this and then we call copyres. And then we do this a couple of times. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This will be 2 and 4 and 8 and 10, 20, 40, 80, and then what? 1B 36. Okay, so we don't need to do this the 11th time because the first sub key is the input key. But I still want to save that in the same array, so we have everything at the same place. So let's move into, let's see, EDX contains the current address. Maybe it's easier to do it like this. We create 10 of these keys, and then just in front here we create let's call this AES key. Reserve 16 bytes. So let's see. Let's move into ECX, the AES key address. And what do we want to move into this? That is the input. So we need to do a move DQU. Well, we can do it here. So we move DQU. Move DQU to XMM2 EBX, the input address. So we want to do the reverse. We want to move into ECX. The XMM2. I think that's the right thing. So first we put inside of this array, we copy the input key, and then we start creating the 10 other subkeys using this output address inside of EDX. So I think that's right. And at each step, we copy the result into the array and we move forward. And when we return, instead of just copying into EX the output, we can use the address of AES key here instead. Because this array right here follows directly after the AES key in memory. And they have the same size. So basically, those two together will be the array then. Alright, let's try this and see what it says. Copyright not defined. Let's do this instead. Almost. Maybe we should choose a different name for this. So let's see. We will give a pointer to one input and we want to return, maybe this is better, pointer to this, and we want to return a pointer to a list of this. Okay, at least compiled. Let's see what happens when we run it. It does not crash, always. That's at least something, right? So let's reload this thing. And let's delete breakpoints. We break at start and we run. Alright, so now we are here. What I am interested in is how the array inside of the memory keeps growing. So let's see, what do we want to check? The AES key, basically. So if we were to do 16bx on the AES key, move EBX, move EDX. So EBX will contain the input and EDX the output. So this is let's do this. If we have 0x %x and we want to take this minus 16 bytes. So this should be the memory location of the first part of the array. So if you do x16bx on this thing, we got a lot of zeros. That's good. And we want to check all 11 of those. So 16 times 11, 160, 176 perhaps. Okay, so here we should see it's growing 2 lines at a time. Each key will be 2 lines. And where do we break? I think by the end of this function. So if we break here, we should hopefully see it grow little by little. But we also need a breakpoint for the first iteration because we are copying, we are not calling the copy res. So basically it will be before this AES keygen assist, which means we will break here. So let's go back to this. Okay, it's all zeros. So now we continue. Here is the first breakpoint. Still zeros. Continue. Okay, the copying didn't work. But as we can see, the first key is generated. And if we continue, so this was the first, and this should be our second. But it starts with 1, 2, 3, 4, 5, 6 zeros. And we have overflowed this quite a bit. Did we calculate this wrong? On 28. Divided by 16. So it should be 16 bytes. Into E6 we move the pointer. Into EDX there is the contents at that location. Which is the saved pointer address. And there we move this. And we add 16 to the pointer. And we put it back. One, two, three, 4, 5, 6, 7, 8. So these are 16. These are 16. 17, 18, 19, 20, 21, 22. So EDX should have this address 05A 6 7 8 9 10. Perhaps something else is modifying those registers. But that shouldn't really matter since we move into memory location pointer. Wait a second, I'm so stupid. This is hexadecimal, 0x16. That's not 16, that's 20 or something. This should be this should be 10. So this will fix the alignment problem. But why didn't it copy our first things? Move it to the contents of ECX. And ECX is ECX is the address of AES key. And we move from XMM2, and XMM2 contains the contents of EBX. And EBX is the address of the input. And the input is a zeroed. Right. The input is all zeros at this point. So let's use another thing here. Let's say we have DD we have 00, 01 02 03. And how many do we have? These are 4, 8, 12, 16 bytes. So we have 3 and 4. 5, 6, 7, 8, 9, A, B, C, D, E, and F. So this is the same input key as we have in our other program, or had. Alright, so let's see. Let's make clean, jump down a little bit, clear the screen, run make, and boom. Let's delete breakpoint. Yes, continue. And we reload. We break at start. And let's do the same again. So EBX is input, EDX is output, and we need to be 16 positions in front of that. So this is the one. Minus 10 this time. So if we do X, let's see, 160, 176 bytes at this location. Good. And we need to have 2 breakpoints. One right before the first AES instruction. And if we disassemble the copy res, so right before we return from this thing. Alright, so let's see if this grows as intended. Alright, we're on the right track, but not quite. Did I calculate this wrong, perhaps? 0, 1, 2, 3, 4, 5, 6, 7. All the way to F. Maybe I did. So here is the input. Here is the output. It's still a bit desynced. Right. We did the same mistake here, of course. Alright, now I believe it should work. So let's do this again. We will do delete breakpoint, continue, yes. And we break at start, run, and we take this address minus 16 bytes, and at this location we want to do 176bx like so, and we need to break just before the first call. And if we disassemble the copy res, we can break at the end of this as well. Alright, so let's go and we check. Alright, so now we have filled this with the input. Let's see if we continue, and now we have this as well. If we go again, So 1 2 1 2 1 2 looks right. So let's go a little bit more. See if we recognized anything. Let's save this thing. So we can compare it to our C code. If we comment this out and we put this back, okay, so the first key is the input key. That matches, of course. Then we have this. It does not really match. But I wonder if it's because any mistake we have done, or if it's because we have found the backdoor. Both things is actually possible. I wonder what this VPS LLDQ is. Shift left by blah blah bytes while shifting in zeros and store results. Okay, so it's a bit shift basically. And P shift D, is that when we swap the values of two registers? Shuffle pack double words. P shift D. XMM1, XMM2, image. Shuffle the double words in XMM2 based on the encoding in im8 and store the result in XMM1. Okay, so it basically copies parts of the register, and this mask right here defines what to copy. But why all this trouble? If we were to go to some page where we can try this online, test AES online. Because I want to see if it's the right result. Well, let's save this, which should be the first result. And let's delete breakpoints. Break at start. So let's see. Here is where we call this first. Let's break it there. And let's see what we have inside of our XMM1. Bunch of zeros. And XMM2 is our input register. And maybe I did put them in the wrong order after all. It's always difficult to think about the big endian, little endian stuff. So let's try this again. Or let's see the result first. So if we step I, we check XMM2 again. We get this. And what did we want to get? This is what we want. But the result should be in XMM1, right? It's still very different. T6AA. So let's try swapping. So let's start here. 1, 2, 3, 4. Let's see, what exactly did we get? 1, 2, 3, 4, 5, 6, 7, 9. Right. So 5, 6, 7, 8, 9, A, B, C. Three. Oh. 1, 2, 3, 4. Well, let's try this and see what we get. So 5, 6, 7, 8, 9, A, B, C, D, E, F. What did I miss? 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Oh, forgot the 0. 1, 2, 1, 2, 1, 2, 1, 2. 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So let's see. We want to break in right before the first AES instruction. And we are looking for this. Continue. Check XMM 1. This is going to be our output register. And we have this in between. put this first one back and let's reorder. So this will be first, then this, and this. And we'll try this again. So we delete breakpoints, yes. We continue. We make. We break at start. We run. And then we enter a breakpoint at the AES keygen assist. Continue there. And we check the info registers XMM1. And this is zeroed because it's our output register and nothing there yet. So let's check our input. Maybe this is right though. What if we were to grab the address of input and do x16bx on this? Ah, 0010. Okay. So now I think I know what we should put here. So this will be a double word and it will contain 00, 01, 02, 03. Then we have 04, 5, 6, and 7. We have 8, 9, A, and B. And we have C, D, E, and F. Alright. So delete breakpoints, yes, continue. Make, reload, break, start, run. And we break it this. Continue. Info XMS1. and this should be 0, and 2. I think this is right. Zero, 1, 2, 3, 4, 5, 6. If we step by and check our output register, this is what we get. Seven six AB 76 AB D6 D6. Maybe it fits after all. Maybe we just didn't read it properly. What if we were to print this plus 1? Where did the 1 go? Okay. If we read from this direction, FE76AB, FE76AB, all the way to D6AA. Okay, we don't get that far. AB, D6, F1. Okay, so this whole 32-bit thing is right. And here we have it again in the right order. AB, D6, 76. Hmm. 3210. Let's try keeping this order like this. Only we start counting from this direction. So we have 0 and 1, and we have 2 and 3. We have 4, 5, 6, 7, 8, 9, 8, B, C, D, E, F. Okay, so this is our input. And if we check the 32-bit things, then we have this. And this is the entire thing. We step I, and we check the output register. And we have this. And we want to compare it to this. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. Right. Compiles just fine. First line starts in 3C, ends in 2B. 3C, 2B. What about the second line? 6-4, E6. It is different. Do we get this 64E6 result when we do the same in the other implementation? Let's see. Yes, 64 E6. So both our two software implementations get the same result. Is it possible that both software implementations are wrong? Or have we actually located the backdoor? That's pretty interesting. Maybe we have. Without even finishing our code. Because it seems pretty unlikely that two totally independent software implementations would be wrong. And it's obviously influenced by this input key, because the four last numbers were identical when we tried our first example. Yeah, I think this will be all for today, but I think we might have found it actually. And if we have, it means that the backdoor is, the key generation is different. It is probably creating either keys based off a key that the NSA has, or it's just weakening the keys. But see you at the next episode. Don't forget to like and subscribe and hit the bell button so you know when it's released. Thank you for watching and thanks for today.